This is the recorded notes for Chapter 3, Part 2, and we're picking up with Newton's second law. So we've talked about Newton's first law, and we've seen that tells us what happens when there's no net force acting on an object. Speed and direction will not change. If there is a net force, the object's going to accelerate. If the object accelerates, then the velocity is going to be changing. So Newton's second law describes the relationship between a net force and the resulting acceleration. A constant net force produces a constant acceleration. The direction of the acceleration is always in the same direction as the net force. Now, what we see with Newton's second law, it shows us that mass and acceleration are inversely proportional. Inversely indicates that the changes in the two values are opposite one another. Basically, if you increase the mass by a certain multiple, the acceleration that's produced by the force is reduced by the same multiple. So the law states that the acceleration of an object is equal to the net force on the object divided by its inertial mass, and you write it, acceleration is net force over mass. You can see we've put the notation that acceleration's a vector and force is a vector. So the way it's written, it shows you that the acceleration and mass are inversely proportional. Inversely proportional, you're going to have one quantity in the numerator and one in the denominator. Now, acceleration and net force are going to be directly proportional because acceleration and net force are both in the numerators. Now, we know we can rearrange formulas. So Newton's second law, most likely you've seen it maybe rewritten as this. The net force equals mass times acceleration. It's very easy to rearrange it and go back to the one we just saw, that acceleration is net force over mass. Okay, so in this rearranging where we have the net force is mass times acceleration, the net force, like I said, is equal to the mass times the acceleration, and it points in the same direction as the acceleration. So basically, when you're looking at the second law, you're describing a relationship between the net force, the mass, and the acceleration. And that gives us a new unit. And that new unit is what we know of as a Newton. We abbreviated with a capital N, and a Newton is a kilogram meter per second squared. You cannot have a force and not have a Newton. So your problem is not going to remind you to check your units. As of now and going forward, you have to make sure you have the correct units. If you don't, you have to do some conversion of units. So we always want that kilogram meter per second. Okay, let's look at this problem. You're asked to find the net force. So we know we need the net force to accelerate a 5 kilogram object. We know our mass is always in kilograms, so we know our mass is 5 kilograms, and we know we have acceleration 3 meters per second squared because we know that acceleration has units of time value squared. So we know it's acceleration, not velocity. So we have force is going to be mass times acceleration. So our mass is 5 kilograms. Our acceleration is 3 meters per second squared. So your force is going to be 15 newtons. And notice we have that kilogram meter per second squared. Okay, let's try another problem. In this problem, we have a 15 kilogram car, and it is traveling along a straight road at 20 meters per second. 2 seconds later, its speed is 21 meters per second. What is the magnitude of the net force acting on the car during this time? Well, we know we are given the mass as 1,500 kilograms, but we're not given the acceleration, but we're given the information to calculate the acceleration. We're given our initial velocity to be 20 meters per second. We're given our time to be 2 seconds, and we're given a final speed of 21 meters per second. And you are looking for the net force. So first off, let's calculate the acceleration. We know acceleration is the change in velocity over the change in time, which is VF minus VI over delta T, which is going to be our VF is our 21 meters per second minus 20 meters per second divided by our time value, which is 2 seconds. So therefore, your acceleration is going to equal 0.5 meters per second squared. And now our force, we know, is mass times acceleration. Our mass is 1,500 kilograms. Our acceleration is 0.5 meters per second squared. So our force is going to be 750 newtons. Okay, let's try another one. So in this one, you're told to use the second law to ask other questions. For example, what acceleration, so we know we're looking for acceleration, would be produced by a 2 Newton net force, so we know our force is 2 newtons, acting on a 5 kilogram object. We know our mass is 5 kilograms. So we know force equals mass times acceleration. So we're looking for acceleration, so we're going to divide both sides by mass. Masses cancel, so acceleration is going to be force over mass. So my acceleration is going to be my force, which is 2 newtons, divided by 5 kilograms. So I'm going to have 0.4, but how do I know the exact units? Well, let's do unit analysis. So we have a newton on top. A newton is a kilogram meter per second squared. And then also on the bottom, we have a kilogram. So our kilograms cancel. We're left with units meters per second squared, which is units of acceleration. Okay, another one. Now we have very small forces can have a tremendous effect on the motion of very small objects. Consider a single electron with a mass of 9.1 times 10 to the minus 31 kilograms. So we have our mass is 9.1 times 10 to the minus 31 kilograms, subject to a single force equal to the weight of a penny. So my force is 2.4 times 10 to the minus 2 newtons. How do I know it's my force? It has units of newtons. And again, you're asked for what's the acceleration. Okay, well, we just solved a problem where we saw acceleration was force over mass. So your acceleration is going to be 2.4 times 10 to the minus 2 newtons over your mass, 9.1 times 10 to the minus 31 kilograms. So your acceleration is going to be 2.6 times 10 to the 28 meters per second squared. Now we want to talk a little bit about mass versus weight. So when you look at mass, what you see is it's a quantity that describes an object's inertia, tendency to resist being accelerated. It describes the amount of matter an object has. We say it's an intrinsic property of an object. And what that means is it's going to have the same value wherever your object is, whatever forces are acting on it. So your mass on the Earth is going to be the same as your mass on the moon. Mass is always going to be in kilograms. Now we look at weight, and notice we say weight's a force. It's a gravitational force exerted on an object by a planet. Your weight is going to be different on Earth and on the moon. Weight is a vector. The vector direction is always straight down. And notice weight is measured in newtons because it's a force. It is not a fixed constant property of an object. And then just to remind you, being weightless does not mean that you are massless. So let's look at weight as a force. Okay. So the force causing a dropped object to accelerate toward the Earth is just the gravitational force. And we call that force the weight of an object. In Chapter 2, we had some ideal situations where we had no air resistance. So what we concluded was that all objects near the Earth's surface fall at a constant acceleration. We know acceleration due to gravity. We use a lowercase g to represent it. If we replace the net force by weight, a capital W, and the acceleration by the acceleration due to gravity in Newton's second law, we have W equals mg. So that tells us that weight equals mass times the acceleration due to gravity. So basically that's a mathematical way of saying that the weight of an object is proportional to its mass and is directed downward. So we'll be talking shortly about free body diagrams. Which you see on the left is a free body diagram. And notice the vector that's labeled W, which is your weight, is pointing downward. Okay, let's do some problems. So first, we want to calculate the weight of a child with a mass of 25 kilograms. So we have our mass is 25 kilograms. We're looking for the weight. We know lowercase g is a constant, so it is on your conversion sheet, and it is 9.8 meters per second squared. So weight equals mg, which is going to equal 25 kilograms times 9.8 meters per second squared. So your weight is going to equal 245. We know weight is operating as a force, so it must have the units of newtons. And if you look up here, we have kilograms, we have meters per second squared, which equals a newton. Okay, our second one, we want to know what is the mass of a dog that has a weight of 150 newtons. And remember, we said g is a constant, which is 9.8 meters per second squared. We know that weight equals mg. We're looking for m, so we're dividing both sides by g. G's cancel on the right, so we have m equals w over g. So we have 150 newtons divided by 9.8 meters per second squared is going to equal our mass, which is going to equal 15 kilograms. Okay, let's do a couple more. What is the weight of a wrestler who has a mass of 120 kilograms? So we're looking for weight. We know our wrestler has a mass of 120 kilograms. Again, G is a constant, 9.8 meters per second squared. We know weight equals mg. So our m is 120 kilograms. G is 9.8 meters per second squared. So our weight is going to equal 1176 newtons. And then lastly, you're asked to find the mass of a car that has a weight of 15,000 newtons. G again is a constant, 9.8 meters per second squared. So we know weight equals mg. Divide G out by both sides. G on the right cancels. So mass equals W over G. So our mass is going to equal 15,000 newtons divided by 9.8 meters per second squared. So your mass will be 1.5 times 10 to the 3 kilograms. We also have something that is known as apparent weight. And we can explain apparent weight by looking at an elevator and having a scale in the elevator. So we have three cases. Case one, there's no acceleration of the elevator. So the person, you have the weight of the person, Wmg, and you have the normal force pointing upward. So basically your scale is going to read your true weight. Now the second case, you're going up in the elevator and you're speeding up. So now notice how much longer your normal force is compared to your weight. So your scale is going to read greater than the weight, than your true weight. Remember, I have this little note saying that the reading on the scale is the magnitude of your normal force. Now, case three, you're going up and you're slowing down. So now notice the vector that's labeled W is greater, so your scale is going to read less than your true rate. Case four, you're going down and you're slowing down, so notice your normal force vector is greater in length than your weight, so your scale is going to read greater than your true weight. Case five, you're going down and you're speeding up. So now your weight vector is greater in length than the normal force, so your scale is going to read less than your true weight. And then finally, case five, it's free fall. Scale and you are free falling together. So there's no contact force between the scale and the person. Everybody's just falling. Okay, this ends Chapter 3, Part 2 of our recorded notes.